Last time, we talked about how computers think in bits and bytes. But how did those simple ones and zeros handle something as abstract as a negative number? It sounds like it should be simple, but the answer is actually a clever trick that when people don't get it, causes some of the sneakiest and most dangerous bugs in all of software. So today, we're diving into signed versus unsigned numbers and why negative values are so darn tricky.
Okay, so let's just put the question right out there. How does a computer, a machine that only gets on and off, 1 and 0, even begin to understand the idea of less than 0? The solution is really elegant, but it comes with some bizarre side effects that can trip up even the most experienced engineers out there.
You see, the heart of the problem isn't really about numbers at all. It's about interpretation. Before a computer knows if a number is positive or negative, it first has to be told how to read the bits it's looking at.
I mean, at its most fundamental level, a string of bits in memory is just a pattern. It doesn't mean anything by itself. Let's say you see 11111111. Is that a big positive number? Is it a small negative one? Could it be a character? Or maybe a shade of red? Without a rulebook, it's just meaningless static.
And that's the absolute key right there. We, the programmers and system designers, are the ones who give the computer that rulebook. We tell it what that pattern means. It's a fundamental design choice, and the path we pick has huge consequences for everything else. That single choice basically splits the world of numbers in two. You have the world of signed numbers, which can be positive or negative, and then you have the much simpler world of unsigned numbers, which can only be positive. All right, let's start in that more straightforward world. Unsigned numbers. The name really gives it away. There is no sign. Every single bit is used for one thing and one thing only, to represent the size, the pure positive value. The very idea of negative just doesn't exist in this world. So let's make that real with an 8-bit number. The smallest possible value you can have is all zeros, which, is 0. The biggest is all ones, and in the unsigned world, that means 255. It's simple, it's predictable, it's efficient. And this simplicity makes unsigned numbers the perfect tool for anything that can never, ever be negative. I mean, you can't have a negative amount of memory, right? You can't have a negative number of items in a list. That's why they're the standard choice for things like memory sizes, array indices, counts, and addresses. Now, let's put these two side by side. With those same 8 bits, the unsigned world gives you a nice, clean range from 0 to 255. But the moment we need to represent negative values, the signed world changes the game completely. Suddenly, those same 8 bits represent a range from -128 all the way to +127. It's the same amount of information, but it's describing a totally different reality. So, how on earth does that happen? How do we get that signed range? Well, computers use this incredibly clever system to make it work, a system called 2's complement. Now, we're just going to focus on the intuition here, not get bogged down in the binary math. In 2's complement, that very first bit basically acts as a sign indicator. But the really ingenious part is how negative numbers are handled. They essentially wrap around from the maximum value. It's a bit weird, but it works. And why do this? Because this whole wraparound design means a computer's processor doesn't need a special circuit for subtraction. It can use the exact same addition logic on both positive and negative numbers. It keeps the hardware simple and the math consistent. But, and this is a really big but, this brilliant trick comes at a price. And that price is a strange, deeply non-intuitive imbalance in the number range. It's an asymmetry. And this one little detail is the source of countless, subtle, incredibly hard-to-find bugs. With our 8-bit signed number, the largest positive value we can possibly represent is +127. But the smallest negative value goes all the way down to -128. See that? The range isn't balanced. It's not symmetrical. There is one extra negative number that has no positive counterpart. And right there, in that one extra value, lies a hidden trap just waiting for an unsuspecting programmer. The bugs that spring from this asymmetry are honestly the most dangerous kind you can have. They are silent. Your program won't crash, it won't throw an error, it'll just quietly keep running, but it'll be producing the wrong result. It corrupts the very logic of your system from the inside out. So, where do these bugs hide? Well, they pop up when you mix signed and unsigned numbers in a single calculation, or when you compare two values that the computer is interpreting in totally different ways. Oh, and the classic case, an integer overflow, where a number gets so big it wraps past the maximum positive value and bam, instantly becomes a large negative number, completely shattering your assumptions.
It's really tempting to just dismiss all this as some low-level detail that only hardware engineers need to worry about. But that is a massive mistake. This issue cuts to the very heart of how we design correct and reliable algorithms.
Think about it. If you don't have a rock-solid grip on this concept, your algorithms will fail at their boundaries. You can unintentionally create security vulnerabilities that allow malicious data in. Your tests will almost certainly miss these critical edge cases. And in really complex systems like AI, it can lead to completely unpredictable and just plain wrong behavior.
So if there's one thing you take away from this, let it be this. Signedness is not an implementation detail. It is fundamental to algorithmic correctness. Period.
I mean, what is an algorithm really? It's all about comparisons, ordering, and checking boundaries. Your choice of signed or unsigned directly changes the very fabric of that logic. It determines if your loops terminate correctly, if your sorting actually works, and if your program accesses memory safely. It's that important.
Understanding how data is represented is the crucial first step. In our next explainer, we're going to dive into how it's actually manipulated. We'll explore the fundamental building blocks of all computation, the bitwise operations and, or, XOR, and NOT. This is where the machine truly starts to reason.
So we'll leave you with a final thought to take with you. Now that you know about the hidden asymmetry of signed numbers, ask yourself, which critical edge case, which silent logic corrupting bug is hiding in your code right now?